Okay, hi everyone. Today we will look at frames that are adapted to the surface. So if you recall back when we studied curves, what we had were a certain frame, the Fresnel several frame, which was a certain frame that was adapted to the curve in the sense that if you restrict it to the curve, then you get the t and n b vectors along the curve. So that was a special frame, and we want to use a similar strategy to study surfaces. So that's the topic for today, to study these these frames that are adapted to the surface. The big topic is now for the next few lectures is to study the geometry of surfaces. And the idea here is that we use the Cartan method for the Cartan structure equations to study geometry. Similarly, where we use the Fourier series equation to study geometry. And to divide the curvature and distortion of the curve. So that's the idea. So the basic strategy here is that we put frames on the surface. On the surface that are adapted in a certain way. That in some way reflects the geometry of the frame, of the surface, and then study how they change. Of this frame. So it's exactly the same idea that we used also for curves, where we had a Frenier frame, and then we take the derivative in the time direction. Here we will be a little bit more careful what we mean by change of rate of change. But the idea is the same, like have the Frenier frame, take the derivatives to get some geometrical data like the curvature and the distortion. But here we do it like on the surface. And the basic idea is essentially that we adapt the surface, the frame to the surface by requiring that the first two vectors are in the tangent direction of the surface, and then the other one has to be normal to the surface. So that's the basic idea of like a frame that is adapted to a surface. Moving frame, which is like defined on some open subset. R3. Is adapted to the surface you also consider as a subset of R3. If E3 is normal to S. What does this mean to be normal? Means that that is for if you have E3 at a point P and you take an arbitrary tangent vector of the surface, you always get 0 for all points on the surface for which also the frame is defined, and for all tangent vectors to that surface. We have the third vector, the surface, and then the third vector is pointing out of the surface. surface in the normal direction. So that's E3. Somewhere that is orthogonal to the surface. So as a consequence, we have that E1 and E2, they have to be elements of the tangent space because it's two-dimensional and we cut out one direction by this equation. So it can't be like something in this E3 direction can never be the element of the tangent space. So there are only two dimensions left, and because our surface was two-dimensional, we know that these two have to be elements of the tangent space. So in the picture is like you have like these E3 is like something in the normal direction, and then we have these two, E1 and E2, which span the surface. So the idea. The point here is that we might only have like the frame might exist only locally. So like this one is only an open subset. So we might only also get like this frame on a local patch on some certain open subset of the surface. So this requirement here that P has to be an element of the surface intersected with the open subset means that we don't require that for all P's. Like it's not like the requirement that like the whole surface can be covered by a frame. But one step would be to at least require that there is a certain normal dimension, and that one would be global. And we have seen that already, that it makes sense for oriented manifold surfaces. So remark 1, 2, 3 might not cover the surface. On the frame on the open subset. But yeah, that's the first remark. And the second one is now we talk about like oriented surfaces, for which we at least have like a global version of the normal direction. So we call as surface that is oriented, and then exists a normal field which was denoted by n, such that which is nowhere vanishing. And there's it's like a certain notation in which like this normal vector field will be very important in the following thing, and especially we would like to we can always ensure if it's like nowhere vanishing, we can rescale it to have unit 1. So like the norm of the vector field for every point would be 1. And then it's called a Gauss map. So that's like just a name. And of P is unit norm map, which is mapping from the surface to the sphere, the Gauss map. So notice that that n is never tangent to s, but always in the normal direction. And the reason why it's like interesting to consider the ones where we have n of p as the unit norm for all points in the surface is because if you restrict a normal vector field, like a moving frame which is adapted, then we have E3 is normal to S, and we have the normal direction, which is normal. That follows that we are n is the Gauss map, and E1, E2, E3 frame on R3 and a certain subset on R3, then this frame is adapted to S if and only if the normal vector, the point equals to so it's like a bit of a question what was first. If you say like, okay, we first have like an orientation which is given by a normal vector field, and we rescale it to get a Gauss map, so like something with unit 1. And then we wonder, do we have a frame which is adapted? Then you already know, okay, like at least one of the vectors has to be given by the Gauss map. And then you only have a choice from E1 and E2 and how to extend E3 off to the outside of the surface. Yeah, so that's one way to see it, if like the Gauss map is first. Another way would be to say like, okay, if you have a frame which is defined, then at least we know that like on the patch where everything is defined, we can define the normal vector field by the third vector. So it's like, yeah, it's like sometimes the Gauss map is first and sometimes the frame is first. And I think it's time for example. So we look at the cylinder. Which is the subset of all points x, y, and z, which we are subject to, we fix the radius to be r. So that's the cylinder. And we would like to discuss, like define like a frame in, say, most of R3, which is adapted to that surface S. So the first step is that we have to find the changing space. So this changing space, and that one is given by all vectors of R3 is tangent to S at the point S, and the point we are, let's say, we call it point X, Y, and Z. If and only if there's a curve C of T, which is in the surface, such that it starts at P and the first derivative at 0 is the vector V. Because it has to be an element of the surface, means in particular if you write like C of T as X of T, Y of T, and C of T. So that's like a general representation by giving just the names of the coordinates. Then this condition here means that we have X of T squared plus Y of T squared equals to the constant R squared. And then if you take the derivative, so dt of this, gives us that 0 equals to X of T times the derivative of X of T at 0, but this one is just V1, so X V1 plus, and the same thing here, we get Y times V2. And that has to be 0, because R is constant. So this implies that an arbitrary tangent vector, sorry, is that say we have like V1 is some constant times Y. So some constant. And if we set it to be because Y is always non-zero, so we can always write this. And if you set V1 to be this expression, plug this one in here, and then solve for V2, what we get is that V2 is equals to minus X of T. So that's the constraint, and V3 can be arbitrary. So that follows that the tangent space of the surface, the cylinder, is spanned by the two vector fields. Spanned by the vector fields. The first one we can say it's just DC, which is the vector field which points in the C direction, which is also logical, right? If you have like the cylinder of this form, and you have the vector field which points always upwards, then this one is clearly tangent to the cylinder. Because like if you point upwards, you can just like have the curve that goes in the normal direction. So that's the first one. And then we have a second one which has like this kind of form. So it's E times multiple, so Vy dx minus x dy. So that would be two vector fields which are always span the tangent space for One DC and part of the so now we want to define the normal vector field. Normal field. And we want something that is like orthogonal to this and to this vector. And you can check easily that this one is given by vector field. So if you take the inner product with DC, you get 0 because this one doesn't have like a DC component. And if you take the inner product with this vector, you have like x times y and then minus yx, that gives you also 0. So you can easily see that this one is a normal vector field because these ones are spanned. And it's not normalized because it has like a certain norm, which is like just happens to be the radius. So if you combine all of that and what we get, we can like have like E1 equals to EC, E2, say like we take the cross product of E1 with E3, or we just take like, for example, the second vector field, which is plus or minus this term, and E3 we take the normalized vector field, the norm, and then we normalize it to x squared plus y squared. And this one is a frame on our free, except for the origin, because at the origin this frame explodes, so that's not well defined, so we have to remove the origin. And if you restrict it to the surface, then you get essentially the normal vector field, and you get, I think that normalize it like this. And if you restrict it, you get like the normal vector field or some constant times this and like same here. So this one is adapted to the cylinder. So the picture is as follows. We have the cylinder, and E1 is pointing like always in the C direction, so that's E1. E2 is pointing essentially along the cylinder, so that's E2, and then the normal direction is pointing just like outwards. So that's the picture of these three vector fields. An important property is here these two vector fields that we say it. These ones are only vector fields on S. So it's important here that we are essentially only have S here. But these ones are like really defined on some larger space of S. So you really have like an extension of these vector fields. They just continue like this, also outside of the cylinder. And it doesn't really matter, like if you're like outside too far here, you could like, for example, start to have like some function in front of DC where you say that you restrict like and make it smaller or something like that. So it's possible to change these frames outside of the surface, and we're mostly interested in what they are doing like directly on the surface or how they change. But in order to say like how they change, we at least need some continuation of this frame a little bit outside of the surface. So that's the main idea, is that they are like at least defined a little bit outside of some part of the surface to make it easier for us to take derivatives. And now I want to give a small lemma that's related to this observation here, is that once you fix the Gauss map, then you already have one E3. So then the question is like, once we have the Gauss map fixed and like the normal vector field, what else can we choose in order to obtain adapted frame? And this formula here that I gave you should give you some idea. Namely, essentially we have like only one choice. Namely, you pick like E3 is given to you as the Gauss map. Then you see E1 is like, I can choose, and then E2 is essentially given by this formula, where you say like once you know E1 and E3, you know that E2 has to be orthogonal to both of them and unit norm. So like essentially you're forced to take this one plus and minus. So that's the idea, is that you essentially don't have any freedom except for this one vector field. We get the following lemma. Which is that S oriented surface with unit norm n. So that's the Gauss map. And then there exists an adapted moving frame on say some open subset in the surface, if and only if there exists a non-vanishing tangent vector field, say here on U. So it's really like tangent to S, so V, P is element of the tangent space. And it's important that it's not non-vanishing. So that's the important requirement here. So let's have a look how this looks like. The first one is, suppose that if E1, E2, so that's the direction that we have on a moving frame. So if E1 and E2 is an adapted moving frame, then E1 of P is an element of TPS and vanishes, never vanishes. So if you have a moving frame, then you know, because like E1 and E2 are like elements of the tangent space as we discussed up here, and we know that they have to be spanning the tangent space and it's two-dimensional, you can never vanish, otherwise it would be only like one dimension. So we know that this one is is well defined over for P. So this one is our vector field. We can also take the E2, but that would be one element that satisfies this condition that like the tangent vector field is nowhere vanishing. So that's the easy direction. And the other direction is that if we have nowhere vanishing, vector field in the subset, then we can just set E1 to be V, or we might need to normalize so that we get like a nice orthonormal frame. And E3, we know already that this one has to be En. And then for E2, we have like, we can take, for example, E1 with the cross product and to get and clearly you can check that this one clearly has norm 1, this one has norm 1 by assumption, and then you can check by the normal like product formulas that this one also has normal 1. So this one is an adapted frame, which is defined at least on O. And then you could, for example, extend that a little bit of the surface if you want to. So what we see is that like the consequence is that like locally an adapted frame always exists, but globally it may not exist. So an example would be, for example, the sphere. What we already learned is that the sphere like has a nice normal vector field which is just pointing outwards to the sphere. But we learned last time with the Harry-Bohr theorem that like whatever vector field you put on the sphere always has at least 1 or 2 points where it vanishes. So there can't be a global frame because if you have a global frame that is adapted to the sphere, then there would be by this lemma would be one vector field that vanishes nowhere on the sphere, but that we have seen as not possible. So that's abstraction that we like. You have like locally everything works, but like globally you might have problems. So that means also all those like the strategies and like how we study certain objects like always will be local. Like we always now focus on some local neighborhood, and on that neighborhood we can like study, for example, how the surface is curved and stuff like that. But like in order to talk about it globally, you usually have to like piece things together on multiple frames, and you can't choose like one nice frame that covers the whole of the surface. And one remark, a parameterized surface always has an adapted frame. So course, we can just choose V to be the vector here that goes in the x direction. You choose a parameterization of the surface, and you just like take, for example, the vector field that points in the x direction, pushed forward to the surface to get like some vector field on the surface with just no variation. So that's a possible choice. Okay. So in the following, we would like to understand a little bit better these frames that are adapted to the surface. And in particular, connect them to the connection forms that we talked about last time. So, suppose we have V1 to be clear is an adapted frame. You see it's defined on open subset of 3. And we have seen last time that the change of the frame is like really important, and we verified the following formula. Actually, it was the definition of the connection forms. Where we have these ones. This one gives you the change of the frame in terms expanded again in the frame again. So for every P, it is here changing vector, which we regard as certain subspace of 3. So that's a nice formula. Like for curves, the nice part was that we essentially have like only one direction which was important, namely the direction of the curve. So that we essentially only needed this formula for t equals like for v equals the tangent direction of the curve. So that made it like relatively simple. Curve. Points on the curve, and for v equals the tangent. It was essentially a and then using this formula we could like recover the curvature and the torsion of the curve. But here it's a bit more tricky. What we now have is essentially if you restrict it to V and like to this open subset, what you get is essentially a one form that is defined locally on the surface. So if you do the same trick. has more information. And it is the one form, 1s, or at least defined locally. So like the problem here is that like for curves we have a canonical direction, namely the direction where the curve is going into. So that's like a canonical direction. But for surfaces, we have two directions, two changing directions. And we have seen already that if you have like multiple directions, then it's usually easier to talk about, put that in the language of differential growth forms, because there we can like, essentially talk about how something changes in one direction or in the other direction. So you keep track of like the variation of the function in all directions. That was like df, which is like a one form. And similar here, we have like a one form that tracks the change of dE in two directions. And then we have, we've seen last time that we essentially have only three different elements in these connections forms, because the other ones were determined by the symmetries. Antisymmetry of omega ij connection forms only independent elements are omega 1, 2, omega 1, 3, and omega 2, 3. These are the only connection forms which are independent. And if you look at this formula up here again, then omega 1, 2 shows you how E1 changes in the E2 direction. So this one is E1 changes in two directions. So the important information that this one is E1 and E2 are only elements of the tangent spaces. So that's something, it's an information about the tangent space of S. Well, it depends on that, because it's like a rotation that says like how much is E1 rotating again to be a different vector, namely in the E2 direction, and that gives us some information only about the tangent vectors. It only involves E1 and E2, and all of them are tangent vectors. But if you look at omega 1, 3, so it's for antisymmetry, it's maybe better to look at where they are like downstairs. So it's the same thing as minus omega 3, 1 and minus omega 3, 2. So these tell you, if you go back to this equation, it tells you how E3 is moving in the E1, in the second and in the third direction. in the first and the second direction. Both of them describe how much V1 changes in V1 and V2 direction. So that means for these things, it's like equivalent. It's like it gives you information about the change of the Gauss network, the normal vector. So in some way, like we have like these three different data, and it carry us quite a different thing. Namely, one of them is just like information about the surface in itself, in some ways. So it really doesn't matter too much of like how you like what is the normal direction, so how the surface interacts with the space around it. But this one is essentially only information about the normal direction. So that one is really dependent of the surface, how it interacts with the surroundings. So the quality is quite different. And in the following, it will be quite important to have this distinction between things that happen only on the surface, which we call an intrinsic, and things that happen like outside of the surface, where you need some information of like how the surface sits in our field in order to talk about the normal direction, for example. So these ones are extrinsic data. This is extrinsic, and this one is intrinsic. Intrinsic means like special to the surface, or like you only need like the surface in itself without needing to worry about like its interaction with the surrounding space. So for curves, we saw that like the curvature and the torsion were the essential information, and they were described by looking at how the B and the N vector field they change, and then you get like formulas for that.